So, why is... Okay, sorry about that. I am very annoyed by whatever. I'm just gonna have to deal with it. We gotta get going. So, welcome to this is our third, I believe, right? Third workshop on control theory. And today we're going to get into stability and control. So, starting off with equilibrium and stability. I'm sure you probably remember this from your whatever physics class you took, but equilibrium is, usually when something is not changing its state. Um, and to be a little bit more explicit, equilibrium is when a system has a specific state that's not changing, which is to say x dot of x star is 0. And you might recall from previously, we used that x star in the case for linearization. That's because oftentimes you're doing linearization about a point of equilibrium. Yeah. Similar kind of thing, quasi-steady state. That's when a system has some but not all variables remaining constant. And just as an example, if you have a skydiver in free fall, they might have a constant velocity, but their altitude is quickly decreasing. So it's quasi-steady. Similar to just regular equilibrium, but not quite. Another important characteristic is stability, which is, for each point of equilibrium, is the tendency of a dynamical system to return to that point, even when there's disturbances. And you can see we have the very classical example of this on the right, of different positions a ball can be in. If a ball is at the bottom of a hill, it will naturally tend to return to that point of equilibrium where it's not moving. If you try to push it out, because gravity will pull it back down into the pit. Contrary, if you have a ball at rest at the top of the hill, it's in equilibrium, but if you disturb it, it will then roll down the hill and leave equilibrium. And then you also have neutral, where if you push it, it just goes into a constant roll, into a quasi-steady state, that is. In general, stability is desirable since it leads to predictable behavior. It's usually something we're aiming for in control design. Just a couple stability properties. You don't necessarily need to remember all of these perfectly. You can always come back and reference this later. The zero input response of a system, that's the tendency of a system to settle to an equilibrium when the initial conditions are not in equilibrium. It's like if the initial position was halfway up a hill, there's a zero input response that it tends to go down the hill. Static stability is the system's immediate tendency to return to equilibrium after a disturbance. And to use a model rocket example, if a model rocket is caught in a gust of wind and it is statically stable, which I sure hope you're flying it statically stable, it will tend to point back in the direction of flight. That's one of the reasons we design our rockets to have a reasonably high stability so that they fly in the direction they're supposed to. Similar to that, dynamic stability is the tendency over time to return to equilibrium. And so in this case, that includes not just the initial tendency, but as it's moving back, it includes the behavior of that. So higher dynamic stability, that would, you would return to the direction of flight really quickly, but low dynamic stability, you might overshoot and return quickly or begin to oscillate. And finally, transient response, that's kind of just a general term to describe, the transient response of the system is how the system behaves on its way while it's returning to equilibrium. So those make sense just from briefly going over them? Or Okay, if there's no questions, I'll just move on. So with that kind of out of the way, we can go into some actual control laws now. So first, as I mentioned before, the kind of core problem of control theory is deciding what U is. And to select U as our system dynamics play out, we use a control law. And that's essentially just the name for any algorithm that, given the controller's knowledge of the present and past states of the system, it can select U. The primary goal of a control law is to encourage the system to behave in a desired way. Usually this means we want the system to achieve a specific state. And usually control laws take the form of just an equation, but oftentimes they also have things like conditionals, whatnot, and other programming type features. So as I mentioned with the desired state, that's usually the end goal. And to actually achieve this, control laws can create or remove points of equilibrium as well as affect their stability. And, this is kind of done by augmenting the equations of the system dynamics. This is all to get it to what's called the set point, which is the more technical name for the desired state. So for example, with this helicopter, our set point might be that we want the helicopter to remain at a constant altitude. If we have this example where there's no rotors, the helicopter just falls. There's no control input. It is, if we say leave the helicopter to be at 1 mile in altitude, it will just fall because it's not in equilibrium since only gravity is acting. If we have a rotor and the lift cancels out the gravity, now all of a sudden we've introduced a new point of equilibrium where none existed before. So actually, real quick, what for a helicopter where you have you have your lift that cancels out your gravity exactly, what would the stability of that be?
What do you mean by that?
Oh, so just in terms of, if I go back a bit, so we can either have a system that is unstable, stable, or neutral. Kind of going from, here. So I'm not asking for like specific number or anything. I'm just asking for general description of if we were to disturb the helicopter.
You would achieve a undesirable, unsteady state.
How so? I'm curious for your explanation.
The helicopter wants to fall down, but by applying a lift, you're bringing it in a direction that's opposite of what's favorable.
Okay, but so think about it this way. We have, with the lift, it's perfectly balanced out and it's maintaining a constant altitude. But let's say that there's a gust of wind that kind of knocks it down like 10 feet or something. Now, because the lift still cancels out the gravity, it's not going to, obviously helicopters can't do this, but for our simplified example where lift just cancels out gravity, now it's just going to be drifting down because the force is perfectly balanced out, it's not going to, start accelerating back to that set point. So in this case,
it's the neutral state.
Yes, exactly. It's neutral. Think of it as, an air hockey puck. If you bump an air hockey puck, it'll just start moving in a direction since the friction is very low. But okay. Does that kind of make sense with what we're going for here?
Yeah. Also, I have a question that might be a little bit off topic.
Go for it.
But let's say in your scenario where the lift does cancel out the force of gravity and there is this wind that pushes it, and let's say your desirable state is just to remain static and not move in any direction. Like, what type of ways could a helicopter sense that it's moving if it's not accelerating?
So how would it? Okay, so I see what you mean. A helicopter is
Like, what type of sensors would be able
yeah.
to?
So kind of what you allude to. If it's accelerating, that's easy. That's what accelerometers do. But it's a lot harder without any acceleration. Um, Typically, that would require, uh, finding your position relative to something else. And from there you can see if your position is changing relative to that thing, and you can do that in a lot of different ways. Uh, one uh, One very basic way is using ultrasonic sensor, which basically sends out. That's like how a bat senses things. Have you ever seen those Arduino ultrasonic sensors? Kind of looks like two little speakers.
Yeah.
Yeah. Basically that emits a sound wave, and when it listens for the return, and it's able to tell how far away some object is, and that gets your position in one dimension, basically. Um, and there's more complicated things like that, where you can find like, in general, those are called time of flight sensors, which basically determine based on some signal you're sending and getting back how far away you are. There's also things like LiDAR and infrared sensors like that those all work in that same kind of manner. Radar. Um, yeah. You also have, you could use something like barometer, which senses change in pressure to detect whether or not you're moving up and down vertically. And that, obviously that's a pretty common aircraft instrument, because you can sense whether or not you're gaining or losing altitude. But that's also only a one-dimensional thing. Probably the most comprehensive thing for this is GPS, which basically tells how far you away from multiple satellites and calculates your position based on that. Um, so that's kind of the most comprehensive and advanced way to do it. Does that answer your question?
Yeah, it definitely does. Thanks.
Okay. Um, so essentially you can kind of think of this, the control law for our hypothetical helicopter is essentially select a constant u that equals gravity. Um, and that, introduces this neutral stability equilibrium point, but that might not necessarily be desirable. Ideally, we probably want to stick around that area, that altitude, even if we have disturbances. So we want some kind of control law that will change you to make sure we always go back to that set point. So what makes a control law good? Number one, the control input demanded by the control law must be physically possible. We can't just apply a 1 million Newton force to our helicopter instantly. It has to throttle up, throttle down, and whatnot. There's a maximum thrust it has. Um, and we also, we can't just straight turn the helicopter off and go to zero thrust, because you then have to start it up again. So oftentimes you're constrained within a certain range of control inputs. Your controller also should have a reasonable balance between control effort and speed, and that reasonable really depends on what you're doing. In some situations, it might be really important to go fast, but in some situations it might be more important to conserve your effort. And by control effort, I just mean the higher your control input, typically that requires more effort. For example, having your helicopter blade spin faster will use more fuel and expend more effort. Additionally, you also want to be avoiding undesirable stable equilibria. Essentially, you don't want to get stuck with your control law going and keeping you stable, but in the wrong place. In general, we seek a control law that's good enough. There are ways to find the mathematically optimal ways for doing this, but that's typically pretty hard, and we're not covering that here. So yeah, now we'll get on to some actual control design finally, after all this time. So just to kind of start off, there's quite a few common control laws, or so you could use any arbitrary equation, design your own or whatever, but often this isn't necessary. There's a lot of different methods for designing control laws. And there's a lot of research in the field that goes into figuring out robust methods, but they aren't just you just plug in and then you're good to go and then it's done. Otherwise, this workshop would be a lot shorter. Every system behaves differently, which means you need to tune your parameters to get a desired result. So a very simple type of controller is bang bang control. Basically, in this type of controller, you have your U can only ever take on one of two values. Typically, that'll be an on or an off, but not always. That could be like, you can either pick between -10 and 10 or something. You're either speeding up or slowing down. Depends on the context. On the right, you can see I have a graph of what this looks like. Imagine the y-axis as the control. It's only ever on or off. And the simplest way of deciding when to switch between on and off is to, depending on whether or not your x is above or below the set point. There's a lot more sophisticated ways to do this, but that kind of falls into what I was saying previously, that we won't be covering how to find the mathematically perfect time to switch. It was also sometimes called two-step or on-off control. But to look at an example, let's say you have a tank that's filled with chemicals, TM, and as a part of your manufacturing process, you have to keep the chemicals at a set reaction temperature. But you can only turn your heater on or off. So this is a time when, you have your controller, you have a bang bang controller that decides whether or not the heater is on or off. And in this example, you can see on the graph on the right, rather than having it be just flipping at a set point, there's threshold values. So in this case, if you were to exceed 61, that turns off the heater. But if you go lower than 59, it turns on the heater. And so that ends up leading to your system kind of oscillating around the set point. Obviously, you never settle exactly to the set point, but you might not need to. Keeping within plus or minus 1 degree might be good enough for your application. Yeah. So does this concept of doing bang bang control make sense?
Yep.
Okay. So to kind of, I mentioned this last time, but another type of control you can use is proportional control. Essentially what this is saying is control proportional to the error. And when I say error here, I mean the difference between the current state and the set point. So the farther away you are from your initial set point, the greater the error. And we have a general equation for this. U is equal, I guess that should be U of t technically. U is equal to negative Kp times E of t, where E is the error. Kp is the proportional constant. The higher the number, the more aggressive your control. And you can see kind of on the bottom, with the block that's further away from your set point, you have a much greater force than the block that's close to the set point. The reason why we have that negative sign in there is so that your force is pointing towards the set point, or your control input, I guess. you could remove that negative and have the k just be the inverse, or not inverse, the negative value. But this is just this is convention, basically. On the right, we can see kind of what the input response of a PID controller would look like. So in this example, we have our set point and we start from a temperature of 0, and you see it goes up and then it overshoots a little, and over time it damps down. The oscillations get smaller over time. And theoretically, in a mathematical sense, you'll always have some oscillation. But in a practical sense, the oscillation eventually gets small enough that you can't perceive it. So does proportional control, is that kind of making sense?
Yeah, that makes sense.
Would the system be better than Bang Bang?
So, Dasha, I'll say, so it depends on what you're doing. In some situations, Bang Bang can actually be the most optimal way to control your system, but you might need to put in a lot of effort to find what that optimal type of Bang Bang control is. This was actually something really interesting that we covered in the optimal control course I took. That's a graduate course. There were some situations in the course when mathematically Bang Bang was the best possible control you could have. So as an example, let's say you're in a car and you want to get from point A to point B in the fastest possible time. The fastest way to do that would be to always be accelerating or always be decelerating. So basically, you'd go and accelerate for half the distance and decelerate for the other half the distance. And that's a relatively simple example, but if you just did proportional control there, you would take longer to get to point B. So it's very much different tools work best in different situations. So part of control design is knowing what control laws are applicable and then how to actually apply those. I will say, though, proportional control is one of the ones it's very useful in a lot of cases. So to get more exciting than proportional control, we have proportional derivative control. So as I said just on the previous slide, proportional control tends to oscillate forever, basically. In some situations, we want to stop those oscillations beforehand. So what we can do is introduce a derivative term. So we now have U of t equals Kp E of t plus Kd times the derivative of the error. And basically what this says is the faster the error changes, the more aggressive that derivative term gets. And what this kind of lets you do is it lets you kind of slow down as you're getting to your set point. And that can, help avoid overshooting. Does that kind of make sense?
Wouldn't this still cause you to oscillate forever, but just kind of just dampens your oscillation?
So, yeah, it kind of depends on, it depends. So, yeah, this is the kind of thing. It very much depends on what you choose for Kp and Kd, because those constants, those are constants that you get to pick, and what you pick for those, that changes what how the system responds. It changes, the properties, like particularly the transient response of the system. Eventually, once we have Kd control now, eventually the Kp and the Kd terms will be, ideally at your set point, they'll be canceling out, and so you won't have any control input. You'll just be in equilibrium, basically. Does that answer your question?
Yep.
Cool. Okay. Moving on, we get into even fancier. I know I'm kind of going quickly between all these letters here. We now have PID, where we can add an integral term. One thing with PD control is that it's actually possible for a PD control to settle at a particular state that is close but not quite at your set point. And this can happen for different reasons. Sorry. Like external like forces and whatnot canceling things out. But with this, it helps remove that steady state error, and basically that Ki term that increases the control the longer you are away from zero. So yeah. As I said earlier, KP, KD, and KI are all things that you get to pick. Oftentimes, in many simpler cases, you just pick them through trial and error. This is one of the big reasons that we're doing, the simulation stuff that we were doing previously, is because it's very convenient to simulate your system and test your controller in a simulation before applying that to the real system. That allows us to, make all our mistakes on a computer, and then when we put it on the real thing, it's working. At least theoretically, assuming you modeled the system with sufficient accuracy. Each one affects the system in a unique way. You also can kind of mix and match them a little. Depending on the situations, you don't need all those terms. Oftentimes, a PD controller is just good, or a PI controller, or sometimes just I, or just P. You can't actually have or I guess you can, but it's not really useful, a just D controller. The reason being because if you have just the derivative term tends to keep your state constant. It doesn't necessarily tend to move your state towards the set point. So it would very quickly settle somewhere that isn't the set point, basically. But okay, continuing on. So basically, the equations that I kind of covered, that's what we call continuous PID. That operates in continuous time. Just like how we have continuous functions in math. The thing is, though, in order to actually implement this in a simulation or on a microcontroller or something, it needs to be able to be described in code. And when we're writing things in code, that's by the nature of how computers work discrete. We can't have a continuous function there. So we need to modify our controller to be able to work in discrete time. On the right, you can also see that's kind of a general block diagram for a general block diagram for the PID controller. These block diagrams are pretty common in controls. Basically, they're a way of kind of visually describing what a system is like. Does the diagram itself make sense, or do you want me to explain anything from it? Okay. So back to discrete. The actual P component doesn't really have to change for discrete time because, it's just a constant multiplication. It's pretty simple. The integral term, we then have to switch to some type of numerical integration. And that's, we covered numerical integration previously. you'd use some kind of algorithm like that to compute the integral over time. There's also simpler ways of doing it too. D is the more complicated part, since in order to calculate the derivative, that would require us to know the future states of the system. And obviously the controller can't measure where the system will be at in the future. There's ways of getting around this, which we're not going to cover today, but we will in the future. So continuing on, I have an example for you guys all to do. So we're going to get to, if you guys want to go ahead and open MATLAB or something like that, we're going to be doing an example with Newton's law of cooling. So do you ever do Newton's law of cooling in like pre-calc or anything?
Yeah, we also did an ODE.
Oh yeah, I suppose it's pretty popular there. So, I mean, as you know, there is a analytical solution to find t, but what I am looking for you guys to do is to be able to create a model for this using a state space, like with the previous examples, and the goal here is, in our example, we need to, in order to perfectly cook our pastry, we need to maintain a temperature of exactly 72 degrees for some time, with the ambient temperature not being that. And so we have our control input, which we can, add an additional up to 15 degrees per minute of heat to our pastry. And we can vary that, whatnot. And what I'm kind of looking for, I'd like you to kind of try coding some of the different control laws that I just showed on the previous slides and see how they compare. So I'm actually gonna stop screen sharing.
Are we starting at ambient temperature and then trying to achieve the 76?
Yeah, I guess I didn't specify initial conditions. Yeah, I guess you could just assume for your initial condition, it's just ambient temperature, and your goal is to get the pastry to maintain a constant set point temperature. Get it to stay within a reasonable air margin of that set temperature. It's like at most like plus or minus a degree or something.
And we can use either like PID control or like bang bang or multiple.
Yeah, so I think probably the easiest to start out with might be bang bang control, I think. Essentially in code, bang bang control amounts to an if statement. That's more or less what it translates to. Can get a little bit more complicated because you might need to do like if else kind of stuff, but okay. So for your reference, if you want to look at the slides as we're going along, I guess as you're coding things, you can actually find all these slides in the workshop and member resources folder. I'm sure Abby knows where it is. Do you know where that is, Terrence?
Yeah.
Great. Okay. So yeah. So Abby, I guess you haven't gone to watch the workshop from for the second workshop, right?
Yeah, I really only got like 10 minutes into it yesterday, but
Okay. So I think what I want to Terrence, do you want to share your screen? And I'm thinking kind of just to kind of give Abby an example of how we go about simulating the state space. Just so
yeah. Also, I thought I knew what folder you were talking about, but I don't.
I will drop a link to it in
Okay.
in Slack. Oh, yeah, I realized that's a link on my system. Hold on a second. Let me get a less sucky link. Oh, but I got freaking signed to SharePoint. So the two-factor authentication that I use for WPI and for work have the accept and deny buttons flipped. So I've totally like accidentally denied access a couple times. Workshops. Almost. And there we go. Wait, did that work? What the hell? Okay, but you can't see the like gr-hprc files from then on, right?
Oh, wait. I'll just find it on my own. Okay.
Yeah, so I'm thinking we'll start off doing, doing bang bang control first, and then you can try partial, and then if we have time, we can try going into some of the other ones.
Okay. And then so this 15 degrees Celsius per minute would be like our bang bang control would be either plus 15 or minus 15.
So keep in mind.
No, minus would just be off, so no heat.
Yes. So in this case, the oven can't cool anything, so we can only have, in this case of bang bang control, we can only have 0 or positive 15. Those are the only two values we're allowed to use.
Okay.
But first, let's start off with like just modeling the system. So I guess for like just to prove that just to create a model and prove it works, try just doing, setting it at initial temperature that's higher than ambient and see how the temperature decays.
Okay.
And it should look pretty familiar.
So, let's see how we do this.
Now, also, do you mind just, I guess, as you're going on, like kind of explaining your thought process for Abby, just so she can see, like.
So this is our ambient temperature, T naught, and then our T final, our desired temperature. But right now, I'm just gonna try to see if I can model the cooling, just by using this differential equation. Just curious, what is negative 26? Is this just a cooling constant?
Yeah. In Newton's law of cooling, there's just a K there. It's a constant.
Okay. Yeah.
That presumably depends on the material or object you're heating.
Is 26 like the actual number for it in air? Wait, no. It really much depends on the pastry.
This is a very made up pastry. I don't think this pastry exists in real life.
Yeah, because I wasn't sure how you all of a sudden like just knew what the K was.
Yeah, K,
Okay.
that's just in our case, it's an arbitrary value.
Okay. So I'm gonna change the ambient temperature to be TA, and then our initial temperature to be like 50, and then
Oh, so actually, quick side note, one thing that's kind of an interesting aspect of control theory is you can kind of think of that K there as being kind of a natural proportional control. So in some sense, the system has natural control being applied. And one of the interesting things that in my optimal control course that I took, one of the proofs that the professor did was basically proving that the dynamics of a system are behaving in a optimal way. So it's an interesting conclusion. Okay, I'll stop now. You can continue on.
let's see, dt equals.
So for this, remember.
I think I have to make some sort of loop.
Well, so remember what we did last time. We want to simulate this as a state space, which means we're going to want to numerically integrate it. Which
Right.
means
Okay. So you want me to find the
OD45.
analytical solution to the ODE?
So I don't want you to find the analytical solution.
Okay.
Because you can actually just solve that as a differential equation and get just straight an equation for t. But in this case, I want to do numerical integration because that kind of lends itself a bit more to what we're doing. So do you remember doing ODE 45 from last time?
Okay.
Basically, we should set that up with the system. So just as background, Abby, you remember we were talking about numerical integration?
Let's see. What did I do?
In this case, OD45 is a function in MATLAB that does numerical integration for us. So it's similar to it does the same kind of thing as RK4, but it uses a different method. In many cases, OD45 is it's a pretty good algorithm. I don't know if the actual algorithm itself is like public domain. I think it might be MATLAB secret sauce, but I'd have to check on that.
Gotcha. Okay.
So I think X is a vector with two components. Its current temperature and its temperature dot. Yeah.
So in this case, I suppose that might be a more accurate way of doing it. In this case, we're just considering U as just U is just something you can pick. You don't have to worry about like speeding up the rate at which it's heating or slowing it down. So in this case, you only have to consider the temperature.
Okay. All right, because those components have to match with the control vector.
Yes. So in this case, our system is we can fully represent the state of the system using a one-dimensional state vector. There's only one variable we have to keep track of.
That is T.
So, I mean, if it's 1D, you don't even have to actually.
Yeah. Okay.
I mean, I guess it looks nice.
Code. Okay. So going back, our temperature ambient is equal to 26. And then our temperature initial.
Well, I think that 26 is. Oh, wait, no, it is. Never mind. Wait, did I pick 26 for both of those?
Yeah.
Okay, that's what I'm getting confused about.
That's fine. And then, I mean, it should be 20, but it's okay. Let's say it's 50. And then I had to create a initial conditions vector. Initial condition would just be 50.
Yeah. So in this case, because we're working with just a 1D thing, you don't actually need the brackets. Because actually, in MATLAB, everything's a vector. So even if you have just a scalar, that's treated as a 1D vector.
Will still do it if it's just a number.
Yeah, so that's the thing with MATLAB. Everything is a vector.
Right.
Everything.
Right, it's just a 1 by 1. Okay, got it. Oh, it makes sense because then let's say you give ODE 45 a vector, it will just solve it multiple times, essentially.
Yeah, it works on every part of the vector.
Right, okay.
Every element.
Okay, and now I have to write a function.
This is kind of a look at what we were doing last time, Abby. Just so you know what we're looking at.
Okay.
Yeah, so now you have to actually...
function to create the x dot.
Yeah. So how you do it, that's up to you. Yeah, so you have t, x, or t, whatever. So, Mary, you have to take in 2 input arguments.
I do?
Yes.
Oh,
so
right.
Every time, that's the like standard form that OD45 expects you to use is 2 input arguments. One is the time and one is the current state.
Got it. And here it would just be negative 26 tx x minus t ambient.
Yeah. So also, quickly recall, do you remember what we were talking about with scope last time?
Nope.
So we have to make sure that TA is within the same scope as
Oh,
X dot.
right.
Yeah.
It's not in here. So
yeah. So right now T's up, A up's up there. If you want, you can add that as an argument, or you can, just put it there. That's probably the simplest solution.
Okay. And then we have to do
semicolons.
Oh, semicolons. Yes. And then let me bring this over.
We might also want to simulate it for like a little less time than that.
This is seconds, so 100 seconds. And X not.
100 seconds is good. We can decide on a baking time for this pastry later.
Okay. Yes, I did mean that.
Oh, yeah, there you go.
Okay. Beautiful. Okay.
I can plot that.
Plot t and x. Oh.
Do you want to plot that over like just a couple seconds to see if that changes anything? Because I'm wondering if maybe it's like I accidentally made this pastry cool off aggressively fast.
Within a second. Very fast. Oh. It did wait. Oh, let me start at 0 then. Oh wow. 1/10 of a second. All right.
That's a fast pastry. So
wouldn't the K usually? I feel like K values are usually under 1.
You're probably right. Change K to like 0.25. That works good.
Okay.
All right. Excuse my ignorance about pastry cooking.
Oh, it cooled in 10 seconds.
Add another 0.
Okay. I like this better.
Okay.
Okay.
So
now we've modeled this.
Yeah, so this looks correct. Do you guys remember the actual like analytical solution for T?
It's something.
I believe it is e to the something. It's a
e to something.
Yeah, exponential whatever. Yeah, so this looks how it's supposed to. So now we can go ahead and try implementing that control. So remember in the x dot, so you have now you add a plus u there.
in the function here?
Yeah, so that's now part of the system dynamics equation. So now within this function, we need to assign u to some value using trying to follow the control outs we were looking at earlier.
Well, u could either be 15 or 0. So do I do like an if statement within the function?
Yeah, you can do that. That's allowed. It's one of the better ways to do it.
If I don't really know the syntax.
MATLAB, you do like if, and then your conditional, and then enter.
So okay. So
and then end after that.
If your current temperature is less than your desired temperature, which we'll have to put it in somehow. Is it this or this? This.
Nothing. There's no. You just have your conditional. That's the end of the line.
I don't know.
MATLAB's going ham with the spelling suggestions.
What? Okay, and then u equals. U 0.
Then now you need to hit enter again and then put in the end keyword to signify the end of the control structure. Okay.
Does there need to be any like indentation, or will it know this n is assigned with this f? If like, will it know?
Yeah, MATLAB doesn't depend on white space. I know from seeing some pretty terrible code.
Okay.
Yeah, don't forget to put your semicolons in there.
I don't know where. Oh, here.
Mm-hmm.
Okay. And also, this doesn't need to be a vector.
No, it doesn't. Also, probably shouldn't be indented now. And the semicolon should be on the same line.
So this should be over here.
Yep, there you go.
Okay.
So actually, real quick, I just noticed you did this where you put the u as a argument. You don't actually need that because you're deciding u entirely within your system within this function.
Yes.
You don't need that.
Okay. And now it doesn't know.
Get rid of the comma too.
Comma. Yes. And we also have to tell it its desired temperature.
Mm-hmm.
TF equals 72. Initial temperature is this ambient.
Okay.
I have
Well, do you want to try it?
Oh,
look at that. You did control.
Beautiful. Wait, it got there very fast.
Yeah, I'm realizing I probably could have picked better numbers for this. Admittedly, I designed this problem like 10 minutes before this started.
And then it has this like sawtooth type of wave.
Yeah. So I mean, you can see why that makes sense, right?
Yes.
Okay. So I realize. So today's.
Wait, I think in this example, it can't ever overshoot. It always stays under.
Do you want to draw a line right at? Do you know how to do a like horizontal line? So there's actually an easier way to do this. Use the command X line.
Oh, X line. Okay.
You do need to do hold on first, though. so that it stays on the same plot.
Yes.
And then X line just takes one input parameter, which is the place to put it. So in this case, just TF or 72, whatever.
It doesn't know that here.
So Abby, I know the kind of syntax of OD45 and whatnot is unfamiliar for you right now, but is kind of generally what's going on. Does that make sense? Oh, you caught that. Nice one.
Never mind. I guess I was wrong.
Yeah, I think it's kind of making sense. It'll definitely be a lot easier once I go through the last workshop. So
Yeah, last workshop deals a lot more with, the system dynamics and the just modeling a system. And we also, the example I did with Terrence, we did something with more than one state element. So I know we're kind of out of time for today, but I guess my challenge to you is, if you find time, try implementing some of the other types of controllers. Probably, try proportional control and see how that compares.
Do I just guess those constants for now?
Yeah, so that's the thing is we don't have like an equation that just tells you what K should be. And there are like, later on there are methods for, getting to a good value quicker. But oftentimes the easiest way is to just guess and check and see if the system behaves the way you want it to and adjust from there. I guess on another side note too, proportional control, the equation by itself doesn't actually consider the control input. So the equation itself doesn't know that you can't go above 16 degrees per minute or whatever I said. Oh wait, I just realized, did you code 16 degrees per minute or 16 degrees per second? I don't know if you did a conversion there.
I didn't.
Okay, that's probably why it's heating so fast.
Yeah. So it would just be 15 divided by 60.
Yeah. But what was I just saying? But I've lost my train of thought.
It takes forever.
Okay, maybe that's a little too slow.
Wait, does it even? Oh wait, I feel like it doesn't. It can't get there. Whoa, wait.
This
It finds another area to stabilize at.
okay, that's odd.
Yep.
So oh no, I think what's happening is
Wait, it shouldn't. Wait.
I guess
That's when the cooling and heating balances out.
Yeah, so I guess, it's not powerful enough to exceed the natural cooling of our pastry. So it just never makes it up. Okay. Well, it's good to know. You need a powerful enough control input to actually control your system. So this is a good example of limits of control. You can't, there's a limit to how powerful our oven is. Yeah. So yeah. Oh, that's what I was saying with PID. It might say you need to apply like 5 million degrees per second, but that's not possible. So oftentimes if we're using PID, we'll just clip it at wherever our maximum is. But there are more sophisticated methods for control that are aware of the limitations. Yeah. So, okay. Do you guys have any final notes before we finish off for today?
Nope.
nope.
Cool. So in that case, I guess just if you can, try seeing if you can do any other sorts of control methods. If you're feeling very creative, maybe see if you can get that block to move in a particular way. The block from last week. Yeah. Okay. With that, I will finish recording. And then I